Hello, new sixth graders. I've called this video number 2B, a continuation of our look in the previous video at prime numbers. And I believe I said that the work I'm going to be asking you to do will be primarily or exclusively finding prime factorizations of numbers, which we covered in the previous and which you've done before. Today, in this one, just a few miscellaneous items related to prime numbers that I think are pretty cool. First of all, let's make this statement. For all prime numbers greater than 5, of course, the prime numbers begin 2, 3, 5, then 7, 11, 13, and so on. Once you go past 5, which is, of course, prime because the only two factors of 5 are 1 times 5, every other prime number greater than 5 will end in either a 1, 3, 7, or 9. There are 10 digits, but the prime numbers greater than 5 end in one of those 4 digits, 1, 3, 7, 9. Now, to understand this is not difficult. Let me list all of the digits, all 10 of the digits. Um, 0 to 9. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, if a prime number greater than 2 ends in 0, 2, 4, 6, or 8, it cannot possibly be prime because it would have 2 as a factor. Now, 2 is prime because it's only two factors of 1 times 2, but any other even number is not prime because it would have 2 as a factor. The number 84 has 2 as a factor. The number 96 has 2 as a factor. The even numbers, of course, are the numbers that have 2 as a factor and they end in 0, 2, 4, 6, 8. So we can cross those off: 0, 2, 4, 6, and 8. Cross off the even digits because other than 2, no prime number can be even. And here we have the 5. Well, 5 is a prime number, but any number greater than 5 that has a 5 in the ones column, what's true about it? What's true about 25, 15, 25, 35, 45, 55? 3,795? Any number that has a 5 in the ones place has 5 as a factor. So there you go. The only 4 digits left are 1, 3, 7, and 9. I strongly recommend that you look at a list. Google first 100 primes or first 1,000 primes if you want to be crazy. And once you get past 5, just look, scan all those numbers. You will see only 1, 3, 7, and 9 in the ones place. So that's the first sort of neat thing about the prime numbers, and there are some others. I believe in video 2A, I mentioned that there's an ancient proof over 2,000 years old that there are an infinite number of primes. At some point in your math careers, your math lives, maybe you could look for that proof. You know, I've seen many videos on it. You can Google it, proof that there are an infinite number of primes. It may be a little too early for you to appreciate that proof, but at some point you can. It's not that difficult. Now, one thing about math, when I speak about how math is cool, sometimes what I mean is that often some of the famous questions about math and most interesting things are just people looking at things and wondering, saying, I wonder, I see something, I wonder if it's always true. And sometimes when you see something, you see a pattern, some mathematician through the years has been able to prove that conclusively. And I think I told you already, if something has been proven conclusively to be true, then we call it a theorem. Sometimes mathematicians will think something might be true, but someone comes along and proves that it's not true. So that can happen too. And then You don't have a theorem, but at least you know that that thing that somebody wondered about has been proven to be not true. So it can work either way. If you scan through the first 100 primes or the first 1,000 primes, you're going to see every so often some prime numbers that are only 2 apart. Now, once you get past 2 and 3, 2 and 3 are only 1 apart. But once you get past that, you cannot possibly have 2 prime numbers that are consecutive, like 7 and 8 or 10 and 11. That can't possibly be true. Do you know why? It's pretty easy to figure that out. If you have 2 consecutive whole numbers, one of them is even. One of them has to be divisible by 2 or have 2 as a factor and therefore not be prime. And so 2 and 3 are the only 2 prime numbers that are only 1 apart. But there are prime numbers that are 2 apart. For example, if you look at that list of the first 100 primes, you'll see that 41 and 43 are both prime. These are known as twin primes. Twin primes are primes that are 2 apart. Okay? Let me give you a couple of others that I just happened to spot when I was looking at the list of the first 100 primes a little while ago. 179 and 181 happen to be both prime, and they're 2 apart, so they are twin primes. And another one, 419 and 421. Now, particularly if you go first 1,000 primes and you look at that list, you might find some twin primes that have 4 digits, 5 digits. There are many, many examples of twin primes that are very big. I'm not sure what the biggest known twin primes are, but they probably have a lot of digits. So the question has arisen through the centuries, are there an infinite number of twin primes like these? Are there an infinite number of them? Or is it limited? Is it finite? That question has not been answered yet. As I understand it, mathematicians have made progress toward it, but it hasn't been conclusively proven yet that there are an infinite number of twin primes. So if you'd like to make a name for yourself in mathematics, maybe by the time you're old enough, it still won't have been proven and you'll be able to do it. And by the way, because it hasn't been proven yet, it cannot be called a theorem, so it's called a conjecture. The word conjecture in the English language is kind of like a guess. This is known as the twin prime conjecture. Mathematicians think probably there are an infinite number of twin primes, but it hasn't been proven. So there's a long-term homework assignment for you if you are interested. Sometime after you've had extensive math studies through college, see if you can prove that there are an infinite number of twin primes. You'll become very famous, at least within the ranks of math people. For the next little cool fact about prime numbers, I've constructed here a number line that shows some of the multiples of 6, 12, 18, 24, 30, 36. So here's the next statement that I can make. Once you go past 3, for all prime numbers greater than 3, they will all be either 1 less or 1 more than a multiple of 6. Now that seems like an unusual statement. At least when I first came across it, I thought so. Well, every 6 numbers, what we're saying is that all prime numbers are either 1 less or 1 more than these multiples of 6. And like I said, it seems kind of strange, but it really isn't. It's easy to understand. Let's just consider a few examples. Well, when you look at 6, 5 and 7 are both prime. Okay. For the number 12, 11 and 13, 1 less and 1 more are both prime. For 18, you have 17 and 19, both prime. For 24, you have 23 and 25. Now the 25, of course, is not prime, but the 23 is. For 30, you've got 29 and 31. Those are both prime and twin primes, as we said. 36, you've got 35 and 37. Now 35 is not prime, and 37 is. Now, please understand what I'm saying. I'm not saying that every number that's one less or one more than a multiple of 6 is prime. What I'm saying is, if it's prime, it has to be one more or one less than a multiple of 6. It doesn't work both ways. It only works that one way. In fact, I should have prepared, but there must be, I'm pretty sure there are some multiples of 6 where neither one of the numbers is prime on either side of it. Really wish I'd looked into that. Maybe I'll pause the video at some point and see if I can find it. But let's try to understand why this is true. Let me maybe make just a bigger, so I have more room, number line where I have two multiples of 6. Let's use 30 and 36. Now, as we know, and I want to look at the numbers between them, right? 31, 32, 33, 34, 35. There are always 5 numbers between two multiples of 6. The 35 happens to be not prime here, right? Now, on the other side, the 37 is prime, but the 35 is not. Well, just before 35 is 34, and then before that 33, and then 32, and then 31. All right, so this is not a great number line, but here's one multiple of 6, 5 times 6, and 6 times 6. All right, and then in between 31, 32, 30, whoops, I wrote 31 instead of 33 there. 34, 35. Now, this is not prime, but in a sense it could have been, if it's because it's one less than a multiple of 6. Now, if you go 2 back, 34, now that can't be prime. Of course, 34 is not prime, but it never can be prime if you go 2 back from a multiple of 6, because every multiple of 6 is even, right? Every 6, 12, 18, and so on. All of the multiples of 6 have 2 as a factor. So if you go 2 back, that's also going to have 2 as a factor. All right. And now let's go 2 back again to the 32. And cross that out. And also the 32 is 2 bigger than this other multiple of 6 here. We had the 30 and the 36. So what we can do is we can eliminate the number that's 2 more than the first multiple of 6, and then we can multiply the next 2 more after that. So we can always eliminate those because they'll always have 2 as a factor and therefore not be prime. Now, what about the one right in the middle between the two multiples of 6? Well, think about it. If you're going up by 6, then right in the middle, this number has to be a multiple of 3, right? And therefore not prime. The 33 is not prime. Not just in this case, the 33, but every time, whenever you look at two consecutive multiples of 6, the number right in the middle will be a multiple of 3. 3 will be a factor, so it can't be prime. We've eliminated the 3 in the middle here because they either have 2 as a factor or 3 as a factor. And what does that leave? It leaves this one that's 1 more than that multiple of 6, and this one here that's 1 less than that multiple. It only leaves the ones that are 1 away from a multiple of 6, which is what the statement is that I made. Now, again, just because something's 1 away from a multiple of 6 does not guarantee that it's prime. This 35 is not prime. But in some cases, a number that's 1 less than a multiple of 6 will be. And here we have the 31 that is prime. It's 1 more than the multiple of 6. It's 1 more than the 30. So it could have been prime, and it is. Okay? I hope I made that clear. I'll state the rule again. We'll say any prime number greater than 3, because actually 5 works, right? 5 is 1 less than 6. So it's 1 away from a multiple of 6. Any prime number greater than 3 must be 1 less or 1 more than a multiple of 6. Another cool thing about primes. I want to finish out this video, which will be the last part of the second installment. There will only be a 2A, and this one here is 2B. Of course, there'll be a third installment of summer videos toward the beginning of August. But I want to finish this one now with going back to the idea of a prime factorization and taking some shortcuts. And in taking these shortcuts, we might along the way learn some things about exponents. Maybe to start, I'll try to focus on exponents. Now, you know what exponents are. We've talked a lot about the fact that 3 to the 2 power is not 6, and 2 to the 3rd power is not 6. Exponents are repeated multiplication. How about this? Think about this. This is not hard. What is 3 times 3 to the 4th? Well, this is 4 3's multiplied together. 3 times 3 times 3 times 3, and then another one. So isn't this equal to 3 to the 5th, right? This is the number one basic rule of exponents. When we get into high school math, there are rules of exponents. This is one example of the first one. It's really obvious. If you understand how exponents work, it's obvious. You don't really have to memorize it because you can figure it out every time you encounter it. But what about this one? 3 to the 2 power times 3 to the 4th power. Well, 3 times 3 times 3 times 3 times 3 times 3. You got 2 here, you got 4 there. I think that means you have 6 3's multiplied together, and we can abbreviate that like that. 3 to the 6th. Now, you want to speculate? Would you like to speculate as to what the rule is in this situation? Add the exponents, right? The 2 plus the 4 to get the 6. Now, if you go back to that first one, you could say that 3 is the same as 3 to the 1. And then you still get that rule of adding the exponents. 1 plus 4 is 5. Now, please note, in both of these examples, the 3's are the same. The bases are the same. You don't have such a rule or a way to simplify if those big numbers are different. So, for example, if you have 3 squared times 4 to the 3rd, there's no way to simplify that. That's not anything to the 5th power, right? The bases are different, so you just have to work it out. It would be 9 times, I'm pretty sure 4 to the 3rd is 64. You might memorize that someday. So it's 9 times 64, whatever that is. You cannot take the shortcut because these big numbers known as bases are different. You might be wondering now, so what, Mr. LeBoeuf? How does this relate to prime factorizations? I'm going to make it relate. We will begin with this. The composite number 60, its prime factorization is 2 squared times 3 times 5. Please confirm that for yourself. Work it out. Make a factor tree. No matter how you do the factor tree, if you don't make a mistake, you'll get this. Remember the fundamental theorem of arithmetic. The whole number 60 has only one prime factorization, and there it is. Well, what if I asked you to find the prime factorization of 120? There's a famous saying, don't reinvent the wheel. It's used sometimes in a situation where somebody wants to go back and do something from the very beginning without relying on other people's work, things that other people have done, maybe. Don't reinvent the wheel. Use the wheel that's already been invented by other humans to do something better, something different that hasn't been invented yet. You could, if you wanted to, start a factor tree for the 120 to come up with its prime factorization. But here's a wheel that we already have, all right? We know that this is the prime factorization of 60. 120, of course, is 2 times 60. So can you figure out what the prime factorization of 120 is just based on that? Based on the fact that the 120 is 2 times 60, and this is the prime factorization of 60? Okay, I think you've had enough time to think about it. You could pause the video, but I bet a lot of you realize that it's this. 2 to the third times 3 times 5. Notice in the prime factorization of 120, there's one extra 2. And this kind of gets back to that business of the exponents that I talked about before. If we went back here to the prime factorization of 60 and multiplied it by 2 to get the 120, right? 2 times 2 squared is 2 to the third. You can see one additional 2 in here that you didn't have here. Okay? How about this? The prime factorization of 300. Now don't use the 120. 300 is not a multiple of 120. But go back to the 60 again. 300 is what times 60? What do you multiply 60 by to get 300? 5, of course. So the prime factorization of 300 has to have whatever's there for the 60 plus an additional 5. Now the 60 already had 1 5. So you know what the prime factorization of 300 is. You don't have to work it out. You can, I happen to have given you 60. And if you didn't have the 60 already, you'd have to do a factor tree for the 300, but don't reinvent the wheel. Use the information I gave you. And this is showing, you might wonder, and notice for the 300, I've got the same thing that I had for 60, except an additional 5. The fact that there's a 5 squared here, there was only a 5 in the prime factorization of 60, that's an additional 5, because 60 is, 300 is 5 times 60. All right? There's a fine line here. I want all of you to realize that in math, you walk a fine line, and here it is. You got to work. Almost everybody, the vast, vast majority of students, myself included, you have to do some work for yourself to learn the math. Homework, quizzes, I correct a quiz, you get it back, you look at your mistake, and the next time you get it right, that kind of thing. Same thing with homework. You got to do some work. There are a tiny number of geniuses out there that can look at math for the first time and they understand it forever. But us regular people, we've got to do work. So I want you to realize that. But also, you can use understanding of math to make a task easier. Like what I did here, what I was suggesting here. In coming up with the 120 and the 300. If you understand how the math works, if you understand that, if you change this 2 squared to a 2 to the third, you've got an extra 2 here, and the 120 is 2 times 60. You're not being lazy, you're being clever. And that's why I say there's a fine line. And I certainly want you to learn clever things like this to avoid having to reinvent the wheel. But on the other hand, when you're learning something for the first time and you need that practice, I do want you to sort of reinvent the wheel. You got to go back, like when you're learning the multiplication algorithm, learning how to multiply whole numbers. Remember that? Well, human beings already knew that. Millions and millions of human beings already knew how to do that, but you had to learn it for yourself through the practice. So there's that. And then there's also these kinds of things where you can take your growth in math, your ability to understand how things work, and make the math easier. It's okay to make the math easier as long as you're learning it. All right, I think I've done enough preaching for now. So there will be, along with this video 2A and the 2B, there'll be some written thing for you to do. I haven't made it yet. And then you'll be seeing these videos around mid-July, and then I'll have the third and final installment of the summer work sometime in early August. So take care, new 6th graders. I will see you soon in math land. Bye-bye.